Okay, in this video we're going to be reviewing how you can combine basic flows together to get more complex flow patterns in potential flow. Okay, so potential flow, remember, is a branch of fluid analysis where we're looking to obtain spatial distributions of the velocity components, right? And so, what we really hope to obtain are basically functions for u and for v. Here I show them in Cartesian coordinates, but you can also have them in cylindrical coordinates as well, so that you get a very nice detailed figure or detailed distribution for how the velocity changes direction and magnitude across an entire space. Okay, and so in the best case, you can get something like this, which shows you a really detailed view of what the flow looks like. Right? And to do this, we make use of scalar functions known as stream functions. Right. So the main reason for this is that, remember, velocity is a vector quantity, and so dealing with its components, especially once you start working with equations, gets a bit cumbersome. And so we define the stream function where, it's a scalar function, but if you take certain derivatives of that stream function, you can get the velocity components. And what's also special about these stream functions is that they also satisfy what's called Laplace's equation, which is right here, which is a partial differential equation, but most importantly, it's linear. And so for linear equations like this, if you have one function that satisfies it and another function that satisfies it, you can simply add them together, and their sum will also satisfy the original equation as well. Okay, and so you can do this endlessly. And so here I have three psi functions that I'm adding together, but you can keep adding more and more. And so we can leverage this this property here because we already know some stream functions to basic flows, and so we can add them together and combine them to get more complex flows. Right. And so one such flow is, I think the first one that most people learn is combining together a source and a uniform flow, right? And so you have uniform flow coming in from left to right here, right? And you have a source that's right here. And so what's going to happen is that the uniform flow is going to meet together with that source, and it's going to form this what's called a half body, right? And so this red line right here, you can use it to model some kind of solid body, right? And to find its stream function, it's very simple. So you take the stream function for a uniform flow, you take the stream function for a source, and you just simply add them together, right? And so this last step that I did here was I just made sure that they were still in the same coordinate system. And so we have a little bit of a mismatch here because the uniform flow is in Cartesian coordinates, but the source flow is in polar coordinates or cylindrical coordinates. And so I just made the substitution where I swapped y into polar coordinates by saying y is equal to r sine theta. Okay, so now everything is in polar coordinates, and it's we Gucci now. Okay, so the other popular one that's learned is flow around a cylinder, and so this has a lot of applications, and in fact, a lot has been studied about this. And to get this flow around a perfect cylinder, you can combine a uniform flow together with a doublet. And so again, we go through the same process of adding them together, and just for convenience, we kind of swap them into the same coordinate system here. So same thing I did on the last page. Okay, and so remember, for streamlines, the flow can't pass through any of these streamlines. And so, even though this red line right here, technically it's a streamline, so it's a direction, it's a path that the fluid follows, no fluid can pass that because it's a streamline. And so we can use it to model solid bodies. And so any kind of cylindrical or circular object that's going through flow, we can model it with this simple equation here for flow around a cylinder. And we can do a lot with this in terms of, finding out pressures, of course, velocity distributions, things like that. So, this stream function concept and the ability to add together flows to make more complex flows is extremely valuable and one of the biggest strengths of potential flow as a technique.